Welcome to our webinar, Aerospace Innovations in 3D Metrology. Thank you for joining us. My name is Kevin Warwick, and I'm a director here at Scan-Xpress. Before we begin, I'd like to introduce some of the team that was responsible for putting today's content together. Benjamin Singer, our lead metrologist. Aman Singh, business specialist. Joshua Span, applications engineer. And Anthony Petrocco, digital communications. A special thanks to Amigo Engineering. They have recently invested in a GOM Atos cube to validate the components they produce through additive manufacturing. We'll be hearing from them a little bit later on. We're excited to spend the next 45 minutes with you to share with you some of the ways technologies we sell and support and use every day are being adopted by manufacturers, especially those operating in the aerospace industry. We hope you enjoy.
Hello again and welcome. Today we will be discussing 3D metrology technology and applications specifically for the aerospace industry, focusing on engine components, turbine blades, MRO and aerostructures. The need for accurate, precise and traceable metrology solutions are paramount when meeting the needs of the aerospace industry. We will be answering any questions you may have at the end, so please put your queries in the chat window. If the stream drops out at any time, please press the refresh button on the top center of the screen.
Scan-Xpress. We are a sales and service company offering access to a wealth of experience in 3D metrology. Combined, our team comprises more than 40 years industry experience. We take pride in offering solutions to a wide range of industries, especially aerospace, where we solve problems for a variety of applications, some of which we will be sharing with you during this presentation. We are more than just a scanning bureau. We offer software, training, and support, friendly advice on which systems will meet your unique needs. As we enter Industry 4.0, we can also guide you in the adoption of industry-leading automated inspection suites. As Australia's manufacturing heads into a new era of expansion, so are we adding representation in new geographies. With our headquarters in Melbourne, we have recently added services in New South Wales and Queensland. More territories to come soon. Now over to Ben. I'll speak to you all later in the webinar.
GOM, a company of the Zeiss Group, specialise in industrial 3D coordinate measurement technology, 3D computer tomography and 3D testing. From product development to production and worldwide distribution, GOM offers machines and systems for manual and automated 3D digitizing, evaluation software, training and professional support from a single source. In industries such as automotive, aerospace, energy and consumer goods, more than 17,000 GOM system installations are in use internationally. At more than 60 locations and with more than 1,200 metrology specialists, GOM guarantees profound advice and first-class service. Since mid-2019, GOM has been part of the Zeiss Group, which has formed a centre of excellence for optical metrology. With more than 13,000 employees in 50 countries and an annual revenue totaling more than 6.4 billion euros, Zeiss is an internationally leading technology enterprise operating in the fields of optics and optoelectronics. Here we can see a small excerpt from the current GOM install range. As you can see, this technology has been widely adopted in the field of aerospace, with many large OEMs using GOM systems in their manufacture and inspection processes. Companies like Boeing, Rolls-Royce, NASA, Pratt & Whitney and Siemens all have multiple GOM systems in use within their organisation. Now we'll hear from Sebastian Rees from GOM Business Development, who will explain how these systems are used in the industry.
Considering that an aircraft has more than 300,000 parts, it is obvious that high throughput is demanded in order to inspect each component, as these inspections are necessary for each individual component. To suit the demands of this industry, it is very important to have reliable results as well as process safe results. With our systems, we are delivering these demands and suit these demands by having processes in place which are compliant to national and international standards and algorithms. It is as well very important to be in the position to have full field data, which is more towards a new approach rather than just inspecting section-wise. With full field data and complete data of a component, like having a digital twin, it is possible to have more information such like surface defects and overcoming the demands of visual inspection and avoiding these. Having the complete component digitized, you can do certainly your traditional inspection of a single section or of multiple of those as you have the complete component, but you can do as well all sorts of alignment. That might be a balance beam alignment, that might be certainly the 6-point nest alignment, it can be a spring-loaded V-block alignment or any other sort of mechanical alignment which can be iteratively created within the software on a digital twin. With our system you can measure, for instance, a complete blisk within less than an hour or a complete turbine blade within a few minutes. Having this, you have the possibility to cut then as many sections as you want to, rather than just having very reduced number of sections. With GOM Inspect, you have the possibility to do all sorts of inspections on your component. You can do certainly section-wise inspection, so the traditional inspection, such like the mean line, the camber line, leading and trailing edge radii, leading and trailing edge points certainly. You have leading and trailing edge ellipses. You can do all sorts of dimensions, chord length, B-tangential chord length, and all sorts of proprietary inspections you wish to implement. With our software you have the possibility to create any proprietary inspection you want to. You don't need to share that with us or with other customers. You just share it with the people you want to. You create a user-defined inspection principle, you create your own labels, your own report styles, and you share that within the packages common in the new software. With the new software we have enhanced the Smart Teach capabilities in order to have even better positions to digitize the component. Those positions are generated automatically based on your inspections and can be adjusted to your needs. With the new functions in the Smart Teach, you have the possibility to enhance your process and your fixturing by seeing which elements obstruct the view of the system. With the new software, we have also enhanced the inspection of a complete blisk or IBR. Rather than creating thousands and thousands of elements for each individual airfoil, you just do the inspection for a single one or a single section, and you simply transfer this inspection to all other blades and all other components on this airfoil. What can the customer now expect due to the merge of GOM and Zeiss? We are bringing our teams together, we are working closely on the hardware and software side together, we are having a big knowledge transfer, and we try to combine processes and knowledge to bring new solutions or further solutions to our customer.
The Atos 5, 5X and 5 aerofoil are high-resolution optical digitizers which quickly provide precise three-dimensional measuring data for optimizing design and manufacture processes. The performance of the Atos 5 series of scanning systems is particularly effective on glossy surfaces, fine structures and small edges. Using an advanced blue light equalizer, the effect of reflection and background interference is reduced. The high-speed cameras and connections result in up to 12 million data points captured in a few seconds. The Atos 5 can be used in a manual configuration on a tripod or studio stand, or in a fully automated configuration in the Atos scan box. Interchangeable measuring volumes give the potential to scan and inspect parts from individual turbine blades to full aircraft. Optical 3D metrology systems are replacing tactile measuring systems and gauges in many areas of industry. They capture more detailed and easily interpretable quality information about an object with significantly shorter measuring times. The Atos Scanbox is a complete optical measuring machine that was developed by GOM for efficient quality control in a large variety of industries. The Scanbox is an adaptable measuring solution. 5 variants with multiple arrangements can be configured to the customer's exact specifications. Parts as large as 6 meters can be inspected in a safe, fast and accurate manner. Using the GOM virtual measuring room within the GOM Inspect Suite software, measurement positions can be programmed quickly and safely to ensure the creation of accurate and robust data. We can now hear from Lee Griffiths, GOM Business Development for Aerospace. Then we'll have a demonstration of the virtual measuring room within the GOM software.
The Atos 5 is the right sensor choice for turbine blades, nozzle guide vanes, compressor parts like bliss and fan blades. Comparing the Atos 5 to our existing sensors, we've seen improvements in measurement times of around 50%. Blisks measured in around 1 hour, fan blades in less than 20 minutes. The number one advantage of the Atos 5 sensor for this industry is the measurement speed. Data acquisition in 1/5 of a second.
Here we have the GOM VMR, or Virtual Measuring Room. We've got the Atos 5 sensor and Plusbox photogrammetry system. We've also got an IGT blade inside a reference frame. For this demonstration, we're creating the measurement positions using the GOM Auto Teach functions. I've already created some of the aerofoil elements we'll need, including the aerofoil sections and leading and trailing edge points. The GOM Auto Teach will analyse the CAD model and the fixture to create the best possible measurement positions for photogrammetry and scanning process. It will then optimise the path between these measurements to reduce the scanning time as much as possible. For certain features on aerofoils, such as leading and trailing edge points, we need specific measurement positions. This is to capture the highest quality data possible on small features to make sure that we've got good quality measurement data and high accuracy and high repeatabilities. This process will only need to be done once for each part type. The measurement points positions will then be fixed to run on multiple parts or complete gauge studies. So now that's complete, we can see the measurement positions for the photogrammetry and the scanning down the bottom here, and we have the approximate time. So for the photogrammetry, it's just under 4 minutes, and then for the scanning, we've got it at just over 3 minutes. We can run through these measurements and see where the robot will be positioned at each point. So let's see how well we've captured these features. We can see our status bar at the top, and we've got a few errors on our surface points here. Using the teach settings, we can visualize where the data is going to be captured at these points. So here we can see we get good quality data from the right hand side of this point, but we've got an error coming in from the left hand side. Let's bring our fixture back up, and we see that this position is actually blocked by the fixture, and we can't see that trailing edge from these angles. By using these features, we can then adjust the design of our fixture. So for this, we might need to rotate the part in the fixture around by maybe 20 degrees to make sure we've got good angles to be able to capture that data. So using these features, we can not only capture the best quality data, we can actually analyze our fixture design before manufacture, saving time and money. This is the Scan-Box 6130. This is one of the larger Scan-Box options in the series and can take parts up to 3 meters. It also has an integrated pallet loading and unloading system for easy loading of fixtures and parts. For this demonstration, we've got a simple aerospace machine component on a very simple fixture design. So again, we can program the robot for these optimized positions for scanning and photogrammetry using the Smart Teach functions. This will analyze that CAD model and the fixture to position the robot in the best possible place to capture that high quality, high accurate data. So now that's complete, we can see the positions for the photogrammetry and for the scanning here, and we've got the approximate times as before down the bottom. We can run through the quick simulation, first with the photogrammetry. We can actually see the live view of the camera and the data that it can pick up in each part. And then we can look at the scanning process. Again, this is simulating the data that we're capturing at each view. I'm just going to skip forward to the end and we can see the final calculated data. So now that's complete, let's switch off the CAD model and have a look at the simulated captured scan data. So the simulation will work on a worst case scenario. So what that means is it's not going to assume that we can capture data that there's any chance that we're not going to be able to capture in real life. So that means that when we run this program on the live part in the scan box, we'll actually probably capture more data than this. But let's just be sure and add in a few manual positions to capture the data on the back side of this feature here. By holding down Shift and clicking on the surface, I can snap the robot to the measurement position for that surface.
using the auto teach functions, we can flip the robot, move to a nice position where we can see that surface, and using the camera view in the top left hand corner, we can switch between the left and right cameras to ensure we've got good visibility on this surface. Pressing the space bar will add a measurement position and it's going to simulate capturing that data at that position. We can then move the robot using the rotation table, and then the scanner. Again, we'll just click and snap the robot into place. Check that we can see that feature in the left and right hand camera. So we can't see it in the right hand camera, so let's move the sensor around. Press space to add that position. So if needed, we can now optimize the path again to ensure that we're scanning in the lowest possible time.
The ScanBox Series 7, along with the Atos 5, is the perfect system for scanning and inspecting helicopter rotor blades. Having a large field of view while still capturing high-resolution data means the process can be fast and accurate. The data is then inspected against a master CAD file or inspected pre- and post-repair to ensure dimensional accuracy. Surface defect mapping is also used, and any areas that fall out of tolerance can be projected back onto the part for easy identification. Accreditation and verification are at the heart of all GOM systems. The software is accredited by NIST and the PTB. The sensor is controlled by VDI VDE certification, and there are a number of specific optical metrology standards in aerospace and beyond which have conformity from different GOM systems. NADCAP is an industry-managed approach to conformity assessment that brings together technical experts from both industry and government to establish requirements for accreditation, accredit suppliers, and define operational program requirements. This has been an ongoing need in the optical measurement sector, and GOM have an active role in the NADCAP task group. The audit topics include asset care, qualification of these sensors, environment, inspection results, and competence and training.
Now we're going to hear from Michael Bushio, Managing Director of Amigo Engineering. Amigo Engineering have recently adopted the Atos Q, a brand new optical measuring system from GOM. The fast data acquisition of this system is well suited for measuring their additively manufactured components. Then we'll pass back to Ben.
I'm Michael Bushio, the Managing Director of Amigo Engineering. Now, 3D printing being a complex technology, it's certainly made us think more about all the processes involved. and that's highlighted the ability to measure some of these complex parts. Originally, some of the earlier 3D printed parts were quite simple, but as designers were able to open up and free their minds to complex parts, multifunctional parts, so more parts in one that can do various things. It seemed to me that we needed to find new ways of measuring these parts. Lots of curved faces and underlying ledges and very intricate detail. Suddenly the standard measuring instruments weren't really enough. Micrometers and verniers didn't cut it. Our CMM, even which we've had for a number of years, we struggled to measure some of these complex parts, and in fact we would spend a long time programming, and we needed fairly skilled operators to run the CMM to measure some of these parts. Really the programming time, which is just too long. It takes a long time to get it all operational. You could do anything anywhere from hours to half a day, even to for days. We had a turbine blade recently, which we were trying to measure, and it got very, very out of hand. A lot of detail and underhanging ledges. This certainly highlighted the fact that we needed to find a better solution. Well, really, I've watched the evolution of scanners over the years, and I've found them to be a little bit wanting. There's the arm scanners, there's probes and digitisation of those, and the add-ons of laser scanners and that sort of thing, and that's been quite good. But really, to do something at a level of getting enough feedback and data for machining purposes at high level, high tolerances, it hasn't been there. But now we've come across the Atos Q, which has only just been released worldwide, and we're the first ones in Australia to actually get one. We've found that this is just amazing. It's down to 6 microns we can measure to, so that's really highlighted to me. This is the time to get into this, and we can use it for everything we do within the business. Well, really, this is being a world first and being first in Australia was one reason to get the Atos Q, but we were looking really for its level of accuracy, and this, to me, wasn't really available until the Atos Q came out. And the ease of use, I've looked at CMMs and the complexity of how they are to the training you need to go to get to an advanced level to be able to use them well, and with this Atos Q, it's really simple. Within a few minutes you've got a part measured, and the level of detail you get is just second to none. You can't possibly get it from the CMM. Just started developing a small jet turbine engine, and as part of that we 3D printed this part here, and scanning of the aerofoil shapes within this part certainly helped us get to the end result we needed. Previously, trying to use the CMM to try and measure in these little blades and the curved sections and the aerofoil design of the whole part was virtually impossible. Certainly on something this small as well. Even if you 3D machine this, like on a 5-axis machine, you wouldn't get the level of detail you've got in the corners and the fine edges on here. Not impossible, but very hard to do. Whereas obviously 3D printing and machining, and then the ability to scan this and then hand it to the machine operator with data that helps him align it in the machine to find the best setup, because we're after balance on this part. We want it to spin at high revolutions, something like 48,000 RPM, and it's got to be very balanced. So understanding where your 3D printed part is, comparing it to the model and giving that feedback to the CNC machinist is paramount. Yeah, well, the traditional machine parts, some of the parts we do in our factory are quite large. We've got a 4.3 metre travelling column milling machine, and if we've got to measure where our machining is in comparison to other parts of the machining on, say, a large pump base or something like that, it's difficult to figure out. You can use the machine's built-in accuracy to probe it and get measurements off. But if you've got to turn parts several times, you need to really take a measuring tool to the machine. So the scanning offers that ability to do that. We can take the scanner and we can scan the whole part, and we can see things that we could never see before. And it's not just a matter of where a hole is or where an edge is or how flat a surface is. You can get complete comparisons to 3D models as what you've machined. It's outstanding.
Using the new features of GOM Inspect Suite, inspection of blisks and discs can be done in a quick and effective manner. Trend analysis, aerofoil inspection, and 3D throat area measurement is all possible within the GOM Inspect Suite software. The aerofoil-specific inspection features that can be used to generate detailed reports on all critical features of parts. This data can be invaluable for manufacture or maintenance and repair. Here we've got an aerospace bracket which was scanned using the Atos Q. You can see the scan data here. You can have a look at the mesh structure and show that good quality data we can capture with the GOM systems. So let's do some inspection on this part. The first thing we're going to need to do is an alignment. Using the pre-alignment function, we'll just do a global best fit of the two parts together. We can then do some localized alignment, maybe a local best fit or a geometric alignment. Creating features in GOM is always done on the CAD first and then created on the actual. So we can create a cylinder here, a cylinder on this feature, and create a plane in the plane, and then with all of these features, create those on the actual. Create our intersection points and a line between those two. Now we've got everything we need to do a geometric element alignment, and now this part's fully constrained. If we wanted to have an additional best fit, maybe on this area down here, we can select it using the lasso tool. Select the best fit alignment. We'll select the geometric element alignment and have this pre-alignment based on that stable alignment. And now that's added in the tree, and we can flick between the two here. Surface comparison will bring up our 3D color map, and this will show any deviations on the legends on the right hand side and change the scale of those legends, or maybe to an 8 color plot. Show exactly where those deviations are. The Eye Inspect tool holds all of the geometric and GD&T dimensional checks, and it will automatically update depending on which feature we've got selected. So for example, we'll select this cylinder here. We can look at the geometrical checks, and we can see that it only got the features selected that are relevant to the element that we've got here. So we can check the diameter, adjust our tolerance, and create that as a geometric check. If we wanted to create that as a report page, we can use that with the table, create a report page with tabulated view, and export that as PDF. So the last thing we'll do is just have a look at GD&T. So maybe we'll check these two planes here. Again, we'll just construct our features. Let's call this one A, and this one B. Again, we'll create those on the actual scan data. So this first one here, we'll check our GD&T, and it's only got the GD&T features that are relevant to a plane. So let's check flatness on this top one here. We can adjust our tolerance if necessary. Now in GOM, we don't just work with two-dimensional data or simple results as you can see here, we can actually see that as a 3D representation. So we can show the 3D color representation of that flatness check projected back onto the part. And we can use deviation labels to show exactly where that is in and out of tolerance. And then selecting our two planes again, and select this bottom plane and do a parallelism check using the top plane as a datum. Report view there, 3D, adjust our labels, and now that can be exported as PDF.
Here we can see scan data of a mould captured using the Atos Q. We can see the scan data from the movable side of the mould and from the stationary side of the mould. A surface comparison is a great way to start the inspection. You can visually see any areas of deviation. We've got the legend on the right hand side showing that any green areas are generally good, and we have any high spots highlighted by the yellow and red areas, and any low spots highlighted by the blue. We can use a tolerance legend to further analyse this colour map and use deviation labels to highlight any areas of particular interest. Overlaying the scan data and the mesh will further highlight deviations in these areas. One of the great features of the Atos Q is the high resolution data that it captures. We can see this by visually seeing the milling marks on the tool surface. Because the data is such high resolution, not only are these milling marks visible, but we can actually inspect the deviation that they have on the effect of the tool. Again, using deviation labels, we can see that this relates to a few microns in error on that tool surface. This is also visible on chatter marks around the side of the tool here. By using 3D data, we can further inspect other features of this tool, such as draft angle. So here we're analysing the data back to a datum plane, and we can highlight any areas that fall within less than 1 degree from that datum plane. When analysing a tool, it's important to know that both sides of the tool will seal properly. We can do this using inspection sections, but we can also do 3D inspection on the two sealing faces. And again, deviation labels to help analyse those areas. We can create report pages from that, and this can be then exported as a PDF.
Using the manual configuration of the sensors, along with tri-top photogrammetry, very large objects can be captured, including full airframes. Scan-Xpress recently completed the capture of a Cessna aircraft. We can now see a short video outlining this process and demonstrating the final captured data. The digital twin is a powerful tool in MRO and inspection. Capturing a virtual copy of the part leads to endless possibilities and is vital for Industry 4.0. Often in MRO, there are model or master components. These can be scanned and used to compare against, meaning it's not always necessary to have representative CAD data. Surface defect mapping is a new and expanding feature within GOM Inspector Suite to characterize the dents, bulges, delamination and other defects on the components. This process can be completed on wings, airframes or small engine components, as the measuring volume can be changed on the sensor. Scan-Xpress can work together with companies to develop return on investment and business case calculations. This will offset the cost of automated or manual systems against the time saving from current measurement techniques. Comparing GOM systems against current tactile measurements can often see a halving of the inspection time. This, coupled with the increased amount of data and information captured, could be the first step in transforming your measurement process. A recent return on investment calculation showed that a fully automated inspection solution with a cost of around $350,000 would see a return on investment for time saving alone in under 17 months. Along with system sales, training and support, Scan-Xpress looked to solve industry problems and streamline solutions. Recently, a customer approached us with an ongoing problem of inspecting helicoils to a specified industry standard. Using the different measurement systems available to us, we found a number of solutions to this problem are in the process of developing a robust process for ongoing inspection of their manufactured parts.
Now we're going to hear again from Amigo Engineering. Jaden Bushell is going to explain to us how additive manufacturing and 3D scanning is being utilized in the aerospace industry.
Additive manufacturing in the aerospace sector is not a new venture. Emirates Airlines explored additive manufacturing back in 2014 to help produce interior components for their aircraft. During testing, it was found that these SLS printed components are between 9 and 13% lighter than most commonly used aviation plastics. Emirates states that every kilogram costs them $10,000 per year to have in flight. Spread these weight savings across their fleet of over 265 aircraft. We're talking about potentially saving millions of dollars a year just from converting to 3D printed components. This development led to 3D Systems' Duraform FR1200 material getting FAR 25853 compliant and was later Class 1 certified in 2017, approving it for commercial flight. As there are commonly no CAD files available for these components, Emirates uses 3D scanning to reverse engineer components and then uses this mesh file to redesign components to better suit 3D printing. From here they go into rapidly prototyping components before moving into low volume production runs. A good example of rapid prototyping is Airbus. Airbus had a seat component that was no longer available from the OEM and the injection molding tool had been destroyed. They were able to reverse engineer this component and have it ready for use within 1 week. Airbus has found that they can reduce weight on the A380 by up to 1 tonne just by converting to 3D printed parts. This is due in part to a lighter material, but also to the ability to be able to redesign existing components to be lighter and stronger without being limited to conventional manufacturing processes. In 2016, Airbus took this a step further after they received the first 2 production models of the LEAP 1A engine for the new Airbus A380neo. Developed by GE and Safran, the LEAP engine is the first engine to use 3D printed fuel nozzles, which helps to reduce fuel consumption by 15% and lower CO2 emissions by up to 50%. Meanwhile, NASA and SpaceX have both been experimenting with 3D printed rocket engines and components. In 2017, SpaceX tested a jet engine that was made up of over 40% 3D printed parts, and in 2018, NASA successfully hot fire tested its new 3D printed combustion chamber. These huge advancements are helped in part rapid prototyping that is only possible via additive manufacturing, 3D scanning and new simulation programs for optimizing and lightweighting components. Research and Markets has projected that additive manufacturing in the aerospace sector will increase by 23% between 2017 and 2021. As companies realize the massive cost saving and design advantages, of this technology, the industry will continue to shift from conventional manufacturing and seek lighter and stronger components. Amigo Engineering is proud to be a part in the development of the Australian aerospace sector. AS 9100D certified and able to provide the most extensive range of manufacturing capabilities under one roof in Australia. This includes the extensive range of metal 3D printing and polymer 3D printing, advanced CNC machining, and much more. For more information, visit our website or contact us below.
Aircraft lifespans range in the decades, and cabin retrofit is a commonplace occurrence during this time. A full 3D scan creates the digital twin of the cabin and allows us to document the actual layout and dimensions of the aircraft. Reverse engineering can then be performed to design the new cabin components. Using this approach, the new cabin interior is installed with minimal downtime for the aircraft. Part measurement is an airworthiness requirement, and Atos systems come in manual and automated configurations to best match the requirements of the business. Manual setups are preferred for mobile measurements and for efficient scanning in small working spaces. When high throughput inspection volume and reducing the risk of operator influence on the data is required, then the automated solutions are the answer. From the measurement, CAD comparisons are the most commonplace evaluation technique associated with this technology, but traditional inspection reporting is common, and within the toolkit include multiple reporting styles. Advanced inspections are possible, including virtual assembly assessment, flash and gap analysis, surface defect mapping and detection.
Before Josh continues with some information regarding our deformation systems, let's take a look at some Atos application examples. The Black Hawk helicopter. The aim of this project was to upgrade the electronic technology for the Australian Army's fleet of Black Hawk helicopters. As part of the project, BAE Systems Australia needed to establish 3D CAD information which accurately reflects the current state of build of airframe and ancillary equipment. 3D scanning and photogrammetry was utilised to ensure the data was captured within a verifiable accuracy of 0.1 mm. Both internal and external data was captured in the same coordinate system, with the point cloud data being reverse engineered to create a full CAD 3D model of the airframe. Fan blade measurement. The ability to capture high-resolution, full-field data is essential for the application of inspecting large aerospace fan blades. For this project, adaptive fixturing was manufactured for automated inspection in the Atos 5 Scanbox 6 series, with the Atos 5 aerofoil sensor. This results in full data coverage of the fan blade whilst maintaining the high resolution needed for inspection of the leading and trailing edge features. For this part, a root clamp was designed which enables multiple blades to be prepared. This reduces the downtime between measurements.
I am now going to talk about the material testing and motion tracking technology from GOM called Aramis. Aramis is an optical 3D deformation sensor that works on the principle of digital image correlation. 3D coordinates are computed and their changes between subsequent images are measured. The system works by either a stochastic or speckle pattern shown in the top left corner, which can provide full field surface analysis, or by tracking the location of discrete point markers as shown in the bottom left image. On the left, we can see an example of the speckle pattern applied to a specimen under load, and the resulting surface strain has been measured. On the right is an example of a crash dummy on a sled, and the movement of the applied reference markers has been determined. The first example I would like to start with is an aircraft crash test conducted by our American colleagues at Trillion Quality Systems and Justin Little from NASA. NASA performs full-size crash tests with the intention of improving aircraft safety. The speckle pattern on the surface allow the Aramis software to measure the strain and displacements of the aircraft as they impact with the ground. The strain results help NASA understand dynamic effects of the crash on the aircraft structures on various terrains. The 3D displacement map is measured and overlaid on the video to identify structures that experience buckling during impact. One of the advantages of full field strain data is that it can be compared to simulated strain data to provide verification of finite element models. In this example, we compare the measured strain data on a 1500 mm helicopter drone rotor blade against the finite element analysis, and we compare the data from a fixed strain gauges against the Aramis strain data. The image in the top left shows the testing setup of the carbon fiber reinforced polymer rotor blade test. The bottom left shows the simulated geometry of the rotor blade as it experiences bending, and the color plot in the top right is a video of the major strain data in the longitudinal X direction as the load increases on the blade. We can see the pockets of missing strain data near the root of the blade where the strain gauges have been affixed to the blade. The strain gauges were applied in these positions because this is where the simulation indicated would be the locations of the highest deformation. In this video, we have changed the measurement volume of the system to examine only the root region, which allows us to acquire higher resolution localized data. What we can see now is that the root region of the blade has non-homogeneous strain distribution, and that as the load continues to increase, the blade will eventually buckle at the root. The strain distribution in the center suggests that the strain gauge was placed next to the region of highest deformation. Now we can compare the finite element model against the measured strain data. We can see in the full field comparison that the ANSYS simulation did not consider the buckling of the blade that Aramis observed, and we can note in the graph on the right that the strain gauge data in pink missed the location of maximum strain that Aramis measured, which can be seen in the red line where it kicks up at the end. The conclusion from this is that the Aramis DIC system can replace traditional strain gauges, and this will save you operating costs and inspection time in preparing your specimens. We have also seen that you do not need to know beforehand where to measure on your specimen. Everywhere you prepare with your stochastic pattern will be available as measurable data. We can also see the capability of full field verification of numerical results. The Aramis DIC system can provide not only strain, but also 3D shapes and displacements from your measurements. The third example I would like to share with you is of a pointwise measurement on a fan blade experiencing a hammer impact test. The Aramis software can record the fan blade's reaction, and this can be used for the calculation of the operating deflection shape. A series of ultralight reference markers were affixed to the surface of a fan blade. The hammer impact event excited the fan blade with a vibration and allowed the identification of its resonant frequencies. The Aramis system measured the fan's response at 15,000 frames per second. The images analyzed the locations of the reference points in the vibration analysis function within the Aramis software, and the operating deflection shapes were determined. The measured operating deflection shape can be compared to the simulated mode shape or the actual shapes from previous measurements. If any difference is measured in the characteristic resonances over life, then there could be a crack somewhere in the blade, and it may not be suitable for flight. The last case study I would like to share of Aramis systems in the aerospace industry is a multi-sensor setup. Sometimes there is a need to measure multiple sides of a complex component, or if the component is very large, then multiple sensors may need to be used to measure the entire region of interest. And in this situation, Aramis multi-sensor setups can be employed. The setup here can show two Aramis sensors looking at both sides of a landing gear testing rig. This allows for point tracking on both sides, where if only one sensor was used, then only one side of the reference markers could be tracked. This video showcases the live camera feed on the left-hand side, where we can see the landing gear rotating on the testing rig. We can also see the secondary Aramis sensor in the background measuring the other side. In this example, we can see the relative movement vectors indicating the direction that the reference markers are traveling in. The larger vectors also indicate that these points are traveling faster than the points with the smaller vectors. The video on the right shows that we have captured the reference markers on both sides of the landing gear, and that we can animate the scanned model of the landing gear through 3D space. This same configuration was employed to measure the effects of thermal expansion on the geometries of a large jet engine. 9 Aramis sensors were triggered simultaneously, each positioned at angular intervals around the outer shroud, to create a detailed 3D model of the entire assembly, as well as to capture the deformations due to thermal loading sustained during operation. I would now like to talk about a new product we have added to our portfolio called the Gap Gun. The Gap Gun Pro 2 is a handheld and robotic optical measuring system from Third Dimension of the UK. Focusing on profile dimensional inspection, this system can be used to capture gap and flush, radius measurements, scratch and dent, edge breaks, countersink, and welds and seals. Scan-Xpress has recently become the exclusive distributor for Third Dimension products in Australia and New Zealand. We thank Third Dimension for this opportunity, and we look forward to a successful relationship. We've already had success with the sale of 2 Gap Gun systems into Bombardier Rail in Queensland, and we're excited to continue promoting this product. Due to their fast and accurate results and user-friendly interface, gap gun sensors have established themselves as the inline profile measurement tool of choice for OEMs and suppliers alike. Current installations exist in companies such as Lockheed Martin and Airbus, to name a few. We will now see a short video showcasing some of the applications of the Gap Gun Pro 2, and after that I'll pass back to Kevin.
I hope you enjoyed the presentation. We certainly enjoyed putting the content together. As was evident, 3D optical metrology has proven itself capable of meeting the exacting standards of the aerospace industry. The technology has risen to meet a number of challenges: tight tolerances, repeatability, a variety of surface finishes and materials, object sizes ranging from small to large. The solutions include static and handheld metrology tools, powerful, fully integrated inspection software, as well as off-the-shelf automation solutions that are easy to install and integrate. We have seen how key applications have been solved by both GOM and Third Dimension. The industry is growing, and we are excited to be growing with it. New technology is on the way. Please take advantage of our experienced and friendly team and come and discuss your needs. Finally, I would like to say how proud I am of the team for putting this together in uncertain times. Many working from home, well done. A special thank you to Amiga for their contribution. And once again, thank you for attending. Please stay online for the Q&A. We'll be sticking around and answering any questions you have posted. Thank you.